of the workshop in Beyond Standard Model. It is also the seminar of IIP, the weekly seminar. And today we have João Paulo. I met him here in the IIP. He was a master student in Paraíba.
6 years ago.
Yeah. Then.
Oi.
And he recently finished his PhD in Barcelona.
No. Yes, ICC. Instituto de. No. Instituto de Ciencia del Cosmos.
And he will be starting soon his first postdoc at Tsungdao Lee. Today he'll be talking about neutrino cross-sections in the standard model and beyond.
Thank you very much, Gabi. So for me, it's a pleasure to be here because, as Gabi said right now, I was an undergraduate and master student in Paraíba, and I was part of this IIP group, the first one, when Farinaldo started here. And by luck, I traveled to Barcelona and worked with very good physicists like Michele Maltoni, Concha. They are my advisors, they were my advisors. And I started to work on neutrino phenomenology. But not only neutrino phenomenology on oscillation, because this is kind of old, right? So we started to brainstorm, not with Concha and Maltoni, because they are old too, but with the youngsters, like not so young, like Pedro, Machado, Joaquin Kopp. And during the neutrino platform, I was a member of the neutrino platform in CERN this year on February. We started to discuss about what is new on the neutrino field. What could be new to work on neutrinos? Because, usually you have some options. I hope that everyone knows about neutrino here, right? So usually a neutrino oscillates to another flavor. And so this. A neutrino is produced on a source in flavor state, but it's propagate in mass state, right, because of the kinematics, and it is detected on flavor again. And this quantum phenomena is the neutrino oscillation, okay? So for, 30 years, the people studied this phenomena. The main problem is, what we can do now, right? Because these people, Pontecorvo, Smirnov, these old guys, they created this field, they wrote all the theories possible, and now we have nothing to do about this. So the people start to invent. And what was a field that was not explored during this period? Neutrino cross-sections, right? During the 90s, two groups from IFIC in Valencia, Russo, and some guys from SLEC, they started to develop the field of neutrino scattering with the nucleus, right? So you have a neutrino here, and you have a fixed target. The neutrino, it interacts, exchanging some gauge boson, and the question is, what are the types of interactions possible? These people start to study. I'm not following linearly my presentation. So the neutrino interacts with the nucleus. And at low energies, they observed that the neutrino interacts with the full nucleon. With very low energies, the neutrino interacts with the whole atom. It's called coherent scatter in the sevens. At around 100 MeV to less than 1 GeV, the neutrino scatters the nucleons almost entirely. They do not feel the quarks. When you increase the energy, there is a region between 2 and 5 GeV that the neutrino produce a resonance of a delta. Not only delta, there are a lot of resonances, but the dominant one is this delta here. So there is a peak of resonance, and at high energies, the neutrino feels the quarks. So it's called a DIS, deep inelastic scattering. Neutrino interacts with the quarks, so they call parton distribution, the PDFs, so they interact with the PDFs, right? So these guys from the 80s, 90s, mainly during the 90s, they started to study neutrino cross-section for charged current. And why not neutral current? We are going to there. So what happens, let's go back again. A neutrino, usually, how a neutrino oscillation is detected? Usually, you have a source, let me say nova experiment. So you have a beam, a proton beam. This proton beam hits, as Kogolo said, a target, and this target, by QCD interactions, they produce a lot of mesons, shower of mesons, kaons, pions, and these pions are collimated to produce muons dominantly. So these muons are produced and muon neutrinos. And you have this initial flux of muon neutrinos. You have a detector called near detector, like less than 1 kilometer from the source, so they do not participate on the active neutrino oscillation. And 1,000 kilometers after it, or 300 if you go to Japan, the T2K, you have a far detector, very large tank of water, usually, that detects the flavor of this guy. So how this near detector detects neutrinos? They detect via lepton classification, of course, because a neutrino is a ghost particle. So electron is produced here in this detector, the near detector. So you say, look, electron is produced, so probably is a electron neutrino. And if there is not any particle that emits a track before it, or any charge track, you say, oh, this could be a neutrino, this could be other things. But in general, you think this is a neutrino because you have initial flux. So you compare the initial flux with the heated leptons in the initial state. In this experiment, you expect a very high number of muons because you have an initial flux of muon neutrinos, okay? After crossing all this distance across the Earth, you have the far detector, a way larger tank of water of the same material that detects not only muons, but detects muons, electrons, and tau types of events, because you do not detect taus. You detect a cascade, because a tau has a short lifespan, and usually you detect the byproducts of these taus. Okay, so you detect muon, and you detect mu, electrons, and taus. Okay, this is the configuration. And how these processes are possible? Because of the charged current. right? You exchange a W boson, you produce a muon, or electron, or a tau, okay? The main difficulty here is the neutral current. Because the neutral current, I don't know if I have a slide for it. No, I don't have it. So let us use this one. The neutral current does not have a charged lepton in the final state, but it exchanges usually a Z boson, and you have a muon neutrino or a muon or a neutrino in the final state. General neutrino because this mediator could violate flavor, but let's forget about it for now. Okay, so this process is very difficult to measure because you do not have a tag lepton, charged lepton. So usually you call these neutral current processes as background. So this is generating a recoil on the target, and you say, this is not important at all. And this is not important for neutrino oscillation, but it is important to measure flavor change in neutral currents. And if you go to the old experiments, like K2K, like minus, these experiments not even shows the even distribution of neutral current, because they say, who cares about it? And the people, the theoreticians, they follow what the experiment goes, the direction, the phenomenologists. So they usually say, it's good to have a good description of the neutral current, but let us not care too much about the new physics. And they simply left for us, lucky us, to write the theoretical part of BSMs. Because right now, the BSM description of neutrino neutral current scatterings are not even modeled. So we have two jobs right now: to write the theory and do phenomenology. So a lot of publications, a lot of work, and this is what we are doing right now. So let me jump to these two papers. So these two papers, one from Yazaman Farzan, and another from me and Pedro Machado. So we inaugurated the field of studying BSMs on neutrino cross-sections for neutral current. And why inaugurated the field? This is, this is not a lie. Really, we take the NOVA data and studied statistics, analytical statistic to study neutral current interactions, and we call it, we parameterized this new physics using a thing called NSIs. Right? So let me jump to another slide. Sorry, because this I was presenting on the neutrino platform. So this here is an NSI. So the people, Bruno, I think, presented during morning about these effective operators. This is the easiest way to parameterize new physics in the neutrino sector, because this is a six-dimension operator, is a contact interaction, a neutral current contact interaction of neutrinos of different flavors and some fermions at the final state. So let us use these fermions as quarks, okay? So usually this Lagrangian can generate two types of effects: oscillation and scattering. Oscillation, we have a lot of experiments of oscillation. Scattering, this is not possible. There is a high impact effect, but it's difficult to implement, and there is a large systematics related to neutrino cross-section. So in our paper, we did a very, very simple approach. I remember when I was an undergraduate student, my advisor, Carlos Pires, told me that every time you think about a problem, you must think in the simplest way. And after going to simple, you go to the complex. There are some people that go to the opposite side, but I prefer to do as my advisor said, my previous advisor, Carlos. So I showed you that there are a lot of different cross-sections, 3 different cross-sections at the same energy regime, right? Between 2 and 10 GeV. But we did a simple approach. We said, so we have a numerical calculation for the cross-section, a Monte Carlo simulation, NUVRO, for the cross-section. And let us forget about all this complexity and calculate the, imagining the nucleons as free particles. And these nucleons as free particles, we wrote the Lagrangian of a neutrino interacting with nucleons as free particles, and calculated the cross-section of a neutrino interacting with free particles. And we call it number of events should be the number of events with BSM with free nucleons for BSM divided by the free nucleons for the standard model times the numerical calculation for all the complexity of the standard model. I mean, is it fair? Right now we have the answer, because this paper was published last year, and the people from NOVA complained to us, look, this is too naive, this don't make sense, you are rejecting all the complexity. But let me go to this. We are writing a 47-page notes of all the complexity. We are going to publish this paper this year, but we showed that our approach is very good. So we are going to present to the NOVA collaboration. But this approach here is, we are estimating the number of events by the standard model numerical calculation times the ratio between BSM divided by standard model as the nucleons as free particles, okay? And we calculated the bounds for a very difficult parameter, the axial NSI. The axial NSI, I think our friend here knows that these axial NSIs are almost impossible to measure the neutrino axial interaction. Why? Because there are only 2 experiments that measures, no, only 1 experiment that measures this number here. It's called SNO. The problem of SNO is that it's a very low energy threshold, and it's not possible to measure the isospin conserving NSIs, only isovector NSIs. I'm not going to dig too much into the details, but this is inaugurating the field by studying in the simplest way this neutrino BSM. And Yazaman Farzan did something different. She studied all the process separated, but without considering the statistical study of data from NOVA. She was studying like a mock data from Dune, and the statistics was not that good. So right now we are improving our group, myself, Pedro, Julia, and Yazaman is doing a parallel work, and we are advancing this field on generating how to write BSM physics using cross-section. So let me give an example of how to do it. Okay.
It's just that, so this is also the weekly seminar. We have here people from other fields than particle fields. Can you please go back a little, explain what is a neutrino experiment? What is NOVA? Why do you want to calculate the cross-section?
Yes, I need to be. Okay, so a NOVA is this experiment like this. You have a near detector and a far detector. You have a muon in the initial state. And this is NOVA, basically. And NOVA is an experiment in Fermilab. It's a similar, it's similar to Dune. And it has this complexity. there are 3 different cross-sections matching each other, and this is the flux of muon neutrinos from nova. It's peaked around 2 GeV. So the complexity is that all the events are matching 3 different cross-sections for neutrinos, and this is the main complexity. So right now we have this field that is appearing, and we have another field that is already developed. It is this one, the coherent elastic neutrino nuclear scattering. So, as explained, a neutrino will exchange in the standard model the Z boson. This Z boson will, since the neutrino is very low energy, around MeV, with energy de Broglie wavelength very similar to the radius of the atom. So a neutrino will interact coherently with all these nucleons, and in the end interacts with all the nucleus. So it recoils all the nucleus together. And this is another process called SEVENS, coherent elastic neutrino nuclear scattering. Okay, so neutrino interacts with these nucleus, and you could say, look, how these guys can measure a process like this, since it's a neutral current process. And I told you that the experiments usually tags a charged lepton. So how they measure this coherent? Because this coherent is very special. When you have a very heavy atom, like this CSI target, the neutrino interacts with the whole nucleus, and this whole nucleus, the charge of the whole nucleus is proportional, the amplitude is proportional to the A, the number of mass of atoms. So the total cross-section is A squared. So differently from the incoherent interaction that depends on A, the coherent interaction depends on A squared. So if you have a 10 to the minus 38 cross-section centimeters squared, you have a 10 to the minus 38 plus times 50. So you have 50 times more cross-section, and it is possible to detect on this detector, the recoil on this atom. So this is the total cross-section, and you see that the weak charge depends on the number, the atomic mass of this nucleus. And why this is important? Because any other new physics that generates not only flavor changing neutral currents, but any other scalar mediator on this scale of MeVs are very relevant, and you can impose a lot of bounds on this new physics. So you have new physics related to the GeV scale, these 3 processes that you have a lot of data, because these experiments usually generates millions of events, so you can generate statistics from these 3 between 2 and 10 GeV, and you have this kind of events that are around MeV, and they are very important to bound new physics. So this is the range of the experiments. This is the quasi-elastic scattering, the scattering of a neutrino with a nucleon. This is the resonant production, and this is the DIS, deep inelastic scattering. This is the data for charged current neutrino cross-section. And these are the experiments that are looking for it right now. Minus CNGS, NOVA, T2K, and Dussel. What is T2K? It's an experiment in Japan. There is a beam, initial beam, there is a near detector, and far from 300 kilometers, there is another detector called far detector. And these experiments are similar to each other because they are called accelerated neutrinos. They are from the same process of a proton that hits a target, produce pions, and generate muon neutrinos. Okay? So, this is a very interesting field because the people is not writing the formulas. The people is started to explore right now. And if you go to Inspire and search for the neutrino platform report, Joaquin wrote explicitly, we must understand better, develop the field of neutrinos with BSMs. So what is the takeaway of this presentation? I'm not going too far. I'm kind of surfing around the subject. But what is the takeaway? There are a lot of experiments that are going to appear in the next 5 years. Dune in Fermilab, Hyper-K in Japan, Juno in China, Trident in China. There is an update on IceCube. There is Phaser on Europe. There is SHIP, that is an experiment in the US, and this experiment has resolution to detect taus. And since they use a kind of photograph plates, and they could measure not only muon neutrinos, but they can measure even tau neutrinos because they can tag a tau and chip. There are the FCCs. There are a lot of experiments that they are looking for neutrinos at high energies. And why the people started to work on this right now? Because of these experiments right now and on the future. So there is another experiment in Europe called European Spallation Source, and J-Park on Japan. Everyone is looking for neutrino cross-section. This is the new beauties of this next 10 years. And in this field, you can look for probes of new interactions. You can look for sterile neutrinos because you see absence of neutrinos on neutral current processes. You look for sevens and you look for NSIs, a way to parameterize this new physics. So I would like to thank you guys for this, and that's it.
Questions?
So the experimental plots that you showed, they have basically, they're compatible with standard model predictions, right? I'm just wondering what's the connection with your...
This is for charged current,
Okay,
but they does not have for neutral current
I see.
such data. As I explained, it's very easy to measure charged current, but neutral current, it's very difficult because you cannot tag with a charged lepton. So you have this data is compatible. This is not too much compatible. This is not too good because there are a lot of meson exchange, coherent pion production. There are a lot of other things that the people do not understand on the field. So, and there are a lot of form factors and the nuclear physics stuff. So here is very, very complex. And for neutrinos, this is not precise enough. For neutrinos, this is not precise. But this is for charged current. For neutral current,
There are no results.
the data is very short. For example, there is data in this order of 100 GeV because of Phaser that is releasing data right now. There are some data from Minibun. There is some data from Nova, but it is this data is appearing right now. is the main thing.
But with your simple model, do you have like any prediction how much the cross section will be different from standard model?
This toy model, it is only a normalization shift of the total cross section, because you have the total cross section times a normalization shift, not linear normalization shift, but in the end is a normalization shift. What we are doing right now is adding complexity for this structure, because you are deriving all the cross sections individually for each process, adding this new physics. For example, this is for the quasi-elastic scattering with NSIs for axial and vectorial. This is for DIS. This is all the form factors, etc., etc. And here, so we are waiting for new results. The main problem is that when you go to this convention, the NSIs are not anymore for general nucleons. They are for each quark, down, up, and strange. So you can imagine a lot of different parameters. So the main challenge is how to deal with this much of parameters. You have axial and vectorial couplings for each individual quark. You have 6 different flavors, and maybe you can add the CP violation stuff. So the takeaway of this is to use these parameters together with the global fits of neutrino oscillation. Because if you go to the new fit, I'm part of the new fit collaboration, and the new fit uses the same data to explore the global analysis of the NSIs. The main problem is that they are very good to detect vectorial, because only vectorial NSIs add stuff for the probabilities, but not axial, because axial is naturally not coherent interaction. So it's kind of a spin-dependent interaction. So it's only able to be detected on colliding stuff. And coherent, and the only experiment that can look for these guys is SNO. But if you add all this complexity, all this stuff together with all these experiments, like looking not only for long baseline as oscillation, but looking long baseline as scattering amplitudes, and you add all these new experiments like Dune, SHIP, you are going to be able to constrain a lot the space of parameters. So the main idea is to add these new parameters, add these new physics, include in the global fit, and fit this new physics in a precise way.
I thought that also the point of looking at the simple model, that you can also include new physics in the simple model, the coupling of new physics to neutrino at the level of this simple model. Is this something that you did, or?
No, so right now, a guy called Jaime Hofken from, right now he's in Poland. He started to do this, adding in a simple way an interaction of dark matter as a neutral fermion with the nucleus. But you can use the same approach as him for neutrinos, because you just change the label of the particle, the mass of the particle, and he uses a kind of a simple approach for the resonance production. Right now I'm doing resonance stuff with simple approach, because we are together with Joachim Kopp, we are looking only for one specific interaction. The main problem is, if you are too simple, you cannot feel some odd things. So you can, at least in my idea, is you go to simple, you search for new physics, or you bound these parameters. You go to more complex stuff and search for the most interesting cases. And you can play on both sides. I mean, if you are going too simple, the experimentalists do not like it. So they are going to not publish your results. So it's a kind of tricky problem.
More questions? Well, if not, let's thank him again. For those of you that are on the workshop, we still have a